So let's take a look at the integral test. So the formula for the integral test, if you have the series from n equals 1 to infinity of the sequence a sub n. Now since we're taking the integral in the integral test, we need to change a sub n. Since a sub n is in everything in terms of n, we need to change it in terms of x. So I'm just going to say a sub x. And now before we take the integral, the sequence a sub x must meet three criteria. The first one is that it's decreasing over the interval. The next one is it's continuous over the interval. And finally it is positive over the interval. And if it does meet that criteria, then we'll take the integral of a sub x dx, and we're going from the bottom bound to the top bound of the series. So we're going from 1 to infinity. And if the integral is convergent to a value, if it converges, then the series will converge as well. Now if the integral diverges, where you get plus or minus infinity, then the series, we know the series will diverge as well. So looking at number 1, we have the series from 1 to infinity of 1 over n to the 4th power. Now in order to use the integral test, we first have to change the sequence so that instead of it being in terms of n, we need to change it to be in terms of x. So 1 over x to the 4th power. And now we need to see if this meets the three criteria. So it is decreasing, the sequence is continuous over the interval from 1 to infinity, and it is positive or above the x-axis, which means we can use the integral test. So we can take the integral. Obviously our bounds are from 1 to infinity. So the integral from 1 to infinity of 1 over x to the 4th dx. So obviously I can just move the exponent to the numerator and make it negative so that we can use the power rule. We have 1 to infinity of x to the negative 4th dx. And then to integrate this, we just use the power rule. So we add the power by 1 and divide by the same power. So we get x to the negative 4 plus 1, which is negative 3, over negative 3, which can simplify to negative 1 over 3x cubed. And we're going from the interval 1 to infinity. Now since this is an improper integral and you do have a infinity as one of your bounds, you can use limit notation, but I'm just going to skip that and just plug in infinity. So we'll have negative 1 to evaluate this, negative 1 over 3 times infinity cubed minus, when I plug in the bottom bound, 1. So we'll have negative 1 over 3 times 1 cubed, which is just 1. So then we'll end up getting negative 1 over 3 times infinity cubed. The negatives will cancel, so we'll get plus 1 over 3. Now when we evaluate this, infinity cubed is still infinity, and infinity times 3 is obviously still infinity. So we'll get negative 1 over infinity plus 1/3. Negative 1 over infinity is like 0, and we have 0 plus 1/3, which will give us the value of 1/3. So since the integral converges, this means the series also converges by the integral test. Now remember that the only two tests where we can figure out the actual sum of the series are the geometric series and the telescoping series. So we got 1/3 as the value, but that does not mean the series will converge to 1/3. All that tells us is that the series will also converge if the integral converges, and the series will diverge if the integral diverges. So for number 2, we have the series from 2 to infinity of 1 over n times the natural log of n. So once again, we have to change this to be in terms of x. So we have 1 over x times the natural log of x. And so before we use the integral test and take the integral, we have to make sure that it meets the three criteria. We have to make sure that it meets the three criteria. So this is decreasing, it is continuous, and it is positive, or above the x-axis, from the interval 2 to infinity. So now we can use the integral test So you have the integral, obviously our bounds are from 2 to infinity. So the integral from 2 to infinity of 1 over x times the natural log of x dx. And this is just a simple u substitution problem, where our u is going to be the natural log of x, and that will cancel out the x. So if u is natural log of x, then du, or the derivative of u, is going to be 1 over x dx. So then to isolate dx, we just multiply by x, and then dx is going to be equal to x du. So now when I substitute dx in, we'll get the integral from 2 to infinity, and also I can substitute the u in. So u is the natural log of x. I get 1 over x. Since u is the natural log of x, I'll substitute that in for u, times dx, which dx is equal to x du. Notice how the x's will cancel. So we'll get the integral from 2 to infinity of 1 over u du. And the integral of 1 over u is obviously the natural log of the absolute value of u. And u is equal to the natural log of x. So we'll get the natural log of the absolute value of the natural log of x. And we're going from the interval 2 to infinity. Once again, since this is an improper integral with infinity as one of the bounds, I can use limit notation. But I'm just going to skip ahead and just plug in infinity. So to evaluate this, we'll get the natural log of the natural log of infinity minus the natural log of the absolute value, natural log of 2. The natural log of infinity is infinity, and the natural log of the absolute value of infinity is still infinity. So we'll get infinity minus the natural log of the natural log of 2. This is insignificant compared to infinity. So infinity minus an insignificant number will still get us infinity. So this means the integral diverges, which means the series will also diverge by the integral test. So for number 3, we have the series from 1 to infinity of 1 over n squared plus 4. And you can integrate this. So we can go ahead and change the variables. So instead of n, we have x. So 1 over x squared plus 4. And we have to make sure that the function is decreasing, continuous, and positive over the interval, which it is. So now we can use the integral test. With the integral, our bounds are from obviously 1 to infinity of 1 over x squared plus 4 dx. Now this might look a little tricky at first, but really this is the arctangent function. So remember that the integral of 1 over u squared plus a squared dx is going to be equal to 1 over a arctangent of u over a plus c. And since this is a definite integral, we don't need the plus c, but we do need the 1 over a arctangent of u over a. So if x squared is our u squared, then u is going to be equal to x, and if 4 is a squared, then a is going to be equal to the square root of 4, or 2. So to evaluate this integral, we get 1 over a, so 1 over 2 arctangent of u over a, so x over 2. And then we're going from the bounds 1 to infinity. So if I were to evaluate this, let's start by plugging in infinity. We get 1/2 times arctangent of infinity over 2, which is still infinity, minus 1/2 arctangent of 1/2. So to evaluate arctangent of infinity, remember the graph of arctangent looks something like this. And so as the x values increase without bound, it reaches a horizontal asymptote of y equals pi over 2. So arctangent of infinity is going to be pi over 2, so 1/2 times pi over 2 minus 1/2 times arctangent of 1/2. Now think about this, and you can't really calculate it in your head, but you will get some decimal when you plug into your calculator, let's say around 0.4. And so we know that when we subtract these two terms, we'll get a value, a finite value, which means that the integral will converge, which means also that the series will converge by the integral test.